All right, so I am going to drag all of you back to the beginning of the semester, which at this point seems like it was 5 years ago, but it was really just a few months. We took a look at an example that gave us a relationship between position and speed and acceleration, and that was our maglev train. And yes, I know a maglev train doesn't have wheels, but y'all know I can't draw anyway. So our maglev train had a position function, right? And that position function was f of t is 4t squared. And that represented the position in feet at time t in seconds. So at 0 seconds is the initial position of the train. After 1 second, the train is 4 feet along. After 2 seconds, it's 16 feet along. After, that should be a 32. After, should it be a 32? All right, whatever. It doesn't matter. All right, so that was how the train moved. And we discovered after some experimentation that the derivative of the position represented the velocity or the speed of the train. So this is position. All right, so if I know the position of the train at time t, I can find the velocity or the speed of the train at time t. So it would make sense logically if I knew the velocity of the train at time t, I should be able to work this backwards to figure out the position of the train at time t. All right, so going in this direction from here to here, from the function to its derivative, well, is called a derivative. If I know that a function represents the derivative of another function, then moving in this direction from the derivative back is called an antiderivative. Yep, I don't leave myself enough room. Just barely. Is called an antiderivative. Okay, so what we're going to learn in this video is how to take antiderivatives and what they mean, or at least one of their meanings. All right, we're going to do this in terms of the physics, and we're going to look at this in terms of speed and velocity. Position and velocity and acceleration. Okay, so let's go through some basic definitions here. All right, and the first one is a function which we will denote as capital F is an antiderivative of a function that we will call lowercase f. All right, so a function capital F is an antiderivative of lowercase f on an interval if, I would call that interval I, if when I take the derivative of capital F, I get lowercase f. All right, for all the x's in the interval. So I'm just going to say in the interval I. All right, so the basic idea when we're looking at the maglev train function here is I would call this my capital F. All right, so in the case of the maglev train, capital F is going to be 4t squared. So capital F prime of t would be 8t, all right, which is what is being represented here by f t. All right, so we would say that capital F is an antiderivative of f. All right, so 4t squared is an antiderivative of 8t. Okay, all right, so that's how antiderivatives work. All right, you know you have an antiderivative if when you take its derivative you get the function. Now, we can work with this definition for a little while, and that is what I'm going to do just because I need to pull a couple of other little concepts in here. So let me leave that there. And we will go back here. All right, so let's take a look at some functions. All right, if I give you the function f of x equals 2x, all right, and I want to find an antiderivative of that. Well, if I let capital F be x squared, then what I know is if I take f prime, what do I get? I get 2x. All right, which means that f x squared is an antiderivative of lowercase f, which is 2x. Okay, so one of the things you might have noticed every time I say this, I keep saying an antiderivative. I'm not saying the antiderivative. When we talked about the derivative, I always said the derivative, all right, indicating that there is one derivative. If you have a function, you take its derivative, that's the derivative. All right, there is a problem with antiderivatives, all right, and that is they are not unique. So let me explain this. If we take this example that I just wrote down, all right, and we take a look, let's move away from the definition and just stick with this example here. All right, when I take the derivative of x squared, I get 2x. All right, but what happens if I take the derivative of x squared plus 1? What do I get? Well, I get 2x. What happens if I take the derivative of x squared minus 7? Well, I get 2x. Right? So what happens if I take the derivative of x squared plus any constant value? I'm going to get 2x. All right, so I don't get a different antiderivative when I look at 2x. My question is, when we move backwards, which one of these was it? And the truth is you don't know. All right, so when we define the antiderivative properly, all right, we have to define it as a function plus a constant, because when you take the derivative of a constant you get 0. It disappears. You lose information about the original function when you take a derivative. All right, every time I take a derivative and that function originally involved a constant. If I want to back up and recover that function using antiderivatives, I need more information. Okay, so we end up with a theorem from this. All right, and the theorem basically says, I'll write it down in a minute, but let me read it off to you first. All right, it is let g be an antiderivative of the function f. Then every derivative of f must be of the form g plus a constant. Every antiderivative must be of the form g plus a constant. All right, so you know what, let's just go right into the notation for this because that'll make it easier for me to talk about. All right, so the notation for antiderivatives. All right, the book goes on and on using this derivative notation. That just gets cumbersome after a while. All right, the notation for antiderivatives. So when I want to say this is the phrase we're translating, antiderivative of f. All right, we say this. The antiderivative is kind of this curly bracket notation here. And then we say f of x dx, and I'll explain that dx in a minute. Okay. All right, so when we talk about antiderivatives, right, when you actually take an antiderivative, you have to account for that constant that may or may not have been there in the original function. So basically what the theorem says is the antiderivative of f of x dx is capital F of x plus c. All right, that plus c is important because when you take the derivative of this, you get this. Okay. All right, so now let me talk about this dx for a minute. We have some properties of antiderivatives, one of which is if I have an equation, I can take the antiderivative on both sides. Just like if you have an equation, you can take the derivative on both sides. We've done that before, implicit differentiation. All right, so if I have a function that is representative of a derivative, yeah, here we go. All right, so what I can do is look at this as a fraction and multiply both sides of the fraction by dx. So over here I have dy, and over here I have f of x dx. And then I can throw a antiderivative sign on both sides because I'm allowed to do that. And we'll see what happens on this side in a minute, but that's where this notation comes from, all right, is from the fact that this was originally a derivative equation, a differential equation, okay? Just remember, you always have to put it there when you're writing a derivative, and it will always disappear when you take a derivative. Think of it as turning into a plus c. All right. Okay, so we need to take a look at some antiderivatives. All right, so we're going to start with a whole new set of formulas. We're primarily going to stick with power rule formulas here. Okay, for those of you going on to take Calc 2 in this sequence, you'll get some of the other functions that we talked about. All right, but to start with, let's start with some ones that we can figure out. All right, so the first one that I want to look at is what is the antiderivative of a constant. So I have a constant k dx. All right, well, let's see, what do we have to take the derivative of to get a constant? All right, so I'm going to come over here and let's look at some of our derivative formulas. Well, we know that the derivative of a constant is 0. All right, so that's not it because I don't have a 0 there. I just have a constant there. All right, so what's the next thing I did? The derivative with respect to x, well, of x, right? What did we say that was? We said that was 1. All right, so I got a constant, all right, but I got a specific constant. So let's try one more. Let's go one step up here and say the derivative with respect to x of a constant times x. What is that? Well, that is the constant times 1, which is the constant. All right, so when I take the derivative of kx, I get k. Well, that's what I need. So that means when I take the antiderivative of k, excuse me, I am going to get kx, but plus c, right? Plus another constant. All right, so because again, if this had been kx plus 1 or kx plus 2 or kx minus 27, I would still get k here. All right, so this is our first formula. All right, now over here with the derivatives, remember we had that property where we could pull the constant out front. All right, so I could pull the constant in front, and then I am taking the derivative of x, which was 1. So that's how I got k times 1. All right, that's what allowed us to do that, was that property there. All right, I have the same property over here. All right, so as a little, we'll say 1a. Make a little outline here. All right, here we go. The antiderivative of k dx is equal to k times the antiderivative of dx. All right. So again, think about this now as having a 1 in here. All right, because there's nothing there, right? So it's a 1. So how did I get 1? Well, that was taking the derivative of x. All right, which makes this k times x plus c. All right, so k times x plus k times, I'm making this a lowercase c, just so you know, lowercase c. All right, k times x is k times x. K times c is just another constant. All right, so we can just call it by our capital C, all right, that we're using. Okay, so both of these are the same. It's just two different ways of getting to the same place. But what this says is I can pull constants outside the integration sign, okay, the antiderivative sign. All right, so let's get a second formula here, and then we can start working with some stuff. All right, so let's look at the antiderivative of x to the n dx. All right, so remember that was our power function. I'm going to, how do I want to do this? All right, let's do this. Let's look at a couple of derivatives of power functions. All right, so d dx of x squared we already looked at. Okay. d dx of x squared is 2x. d dx of x to the third is 3x squared. And I forgot to close my parentheses. One more. d dx of x to the fourth is 4x to the third. And that gave us, when we were doing this originally, right, our power rule, which is d dx of x to the n is nx to the n minus 1, right? Power comes down, you subtract 1. Power comes down, you subtract 1. Power comes down, you subtract 1, and so on. All right, so if I want to go from this side to this side, what would I need to do? Well, let's look at this. All right, so we already know what that is. Let me go here because it's a little easier to see what we're doing here. If I want to take the antiderivative of 3x squared dx, and I want that to equal x to the third plus c. All right, I'm worried about the x to the third part here. What am I doing from here to here? Well, the 3 has to go away, right? The 3 has to go away. So the easiest way for that to happen is to divide by 3. And then the exponent 2 has to turn into an exponent 3, so I'm adding 1. All right, let's look at this one. All right, if I take the antiderivative of 4x to the third, I know I want that to be x to the fourth. All right, so again, the 4 has to go away, and the 3 has to turn into a 4. All right, if I follow that same pattern down, over here, if I want to take the antiderivative of nx to the n minus 1, and I know that that has to be x to the n plus c, well, then what happens? Well, the n has to go away, and the n minus 1 has to turn into an n, so I'm adding 1. So the basic pattern here is, all right, I add 1 to the exponent. 2 becomes 3, and then I divide by that new exponent. All right, so we add 1 to the exponent. Then divide by the new exponent. So if we apply that up here to this, right, we add 1 to the exponent, and then we divide by the new exponent. All right, and this is the power rule for antiderivatives. All right, so as formulas go, we're going to stick with these two for now. I'm not going to do anything more than just power functions, basically, or sum and difference of power functions, which is what we'll get to next. All right, so we had this little sub-rule here that said that I could pull a constant outside. We have another sub-rule over here that says if I have the sum or difference of functions, I'll just write it in general. So if I have f of x plus g of x, I don't know what my problem is with closing parentheses today, dx, I can take the antiderivative term by term. So I can take the antiderivative of f of x dx plus the antiderivative of g of x dx. And how I take those individual antiderivatives is going to be, for right now, with this power rule. Okay, combination of this and this. Okay, so let's take a look. Oh, that's right. It doesn't like that finger. Let's take a look at some examples here. I'm just going to run to the homework set. Give me 1 second. And I'm going to run through some of the even numbers for the homework set, which I will post when I post this video. Okay, so again, using these two rules is what I want to do. All right, so that means that I have to be dealing with power functions, which means no notation, no square roots, nothing like that. All right, everything has to be in terms of numeric exponents, and they have to be basic power functions. All right, we'll get to more complicated types of power functions later on, but for right now, all right, so I am going to look on page, what page am I on in the book? 418 in the book. All right, so I'm going to pull some problems from page 418. And let's start with some basic power functions here. So let's start with number 12. All right, so number 12 says take the antiderivative of 2x to the 5th dx. All right, so in terms of steps, I'll step through this. All right, the first thing you want to notice here is you've got a constant, which means I can pull the constant in front so that I just have the power function part inside. All right, then my first rule says I take the constant times the antiderivative of this. Now again, this is a power function, so I use the power rule for antiderivatives, which says I add 1 to the exponent and divide by the new exponent, and then I say plus c. All right, so again, like most of our problems, that's the end of the calculus. The rest is just simplifying the algebra. And what I can do here is reduce that down. So I get x to the 6th over 3 plus c. Keep in mind, you could also write this as 1/3 x to the 6th plus c to have a proper power function notation. As far as I'm concerned, either one of those is fine. What you do with it is going to depend on what we need to do with it. All right. How about... Ooh, I just thought of something. All right, let's do another example, and then I'll do my how about. All right, let's take a look at number 14. Number 14 is the antiderivative of 3t to the minus 7 dt. All right, notice your differential, your differential here has to match in variables. So if I'm using x, I'm using dx. If I'm using t, I'm using dt. All right, so I have a constant, which I can pull in front. It's the antiderivative of t to the negative 7 dt. All right, so my power rule says, oh, first I have to do that, right? So my power rule says I take my variable, I add 1 to the exponent. So when I do negative 7 plus 1, I get negative 6. And then you divide by that new exponent, plus c. Right? And then reduce your fraction if you can, right? I can reduce that. And I will have t to the negative 6 over negative 2. So I'm going to put the 2 there and put the negative in front, plus c. All right, or if you want to write it as a proper power function, negative 1/2 t to the negative 6 plus c. Again, either one is fine. All right, I want to back up here for a minute because I want to point something out here. Take a look at this formula. All right, we have a potential difficulty here with this, don't we? Right, because I'm dividing by n plus 1. If n plus 1 is 0, then I have a problem because I can't divide by 0. So what is going to make n plus 1 0 here? Well, if I take out n plus 1 and I set it equal to 0, I get n equals negative 1. All right, so this formula is valid as long as n is not equal to negative 1. All right, so I'm going to remove this out of here. Or not. Okay, doesn't want to erase. Oh, I know why it doesn't want to erase. Hang on a second. Now it will erase. No, it won't. Okay. All right, I'm not going to take that out. All right, I'm just going to make a note up here. All right, that n can't be -1. All right, if you recall, all right, the function x to the -1, what is that the derivative of? Well, x to the -1 is 1 over x. Right, so let's put a third rule. I'm going to squeeze a third rule in here. It comes up a little bit later in the chapter, but I'll do it now. And that is, what is this? All right, well, let's look at that for a second. That is 1 over x. All right, and what is 1 over x the derivative of? That was one of the last things we did before we got into this section. All right, 1 over x is the derivative of the log function. Right, so this is ln of x. Now, I have to do one thing, and that is throw absolute values around the x. We literally will talk about that later. All right, so if you have x to the -1, all right, or you have 1 over x, then that does not get done with the power rule because that would cause a problem. That is the antiderivative of the log, okay, or the derivative of the log. So the log is the antiderivative of x to the -1. Okay. Let me go back to where are my problems? There are my problems. All right, so let's take a look at what else can we do here. Ooh, just because I know I'm going to get asked. Let's take a look at number 16. Because I know how much you all love fractions. Number 16 is 2u to the 3/4 du. All right, so again, remember your differential term here has to match your variable. So u du. All right, so I bring the constant out front. All right, so my power rule here now says I take the variable, I add 1 to the exponent, and I will, because this is a fraction, actually write that down. Okay, plus c. All right, so 3/4 plus 1, this would be 4 over 4, so that's going to be 7 over 4. So that is going to be 2 times u to the 7/4 over 7/4. All right, plus c. And then I have to simplify this complex fraction, so I'm going to pull this up and flip it. So that becomes 2 times 4/7 u to the 7/4. All right, and then that's 8, so this is going to be 8/7 u to the 7/4 plus c, like that. Okay. One of the things you can do if you have a fractional exponent is, rather than writing this step down, if you want to just jump right to that step, that's fine. But again, it's just how comfortable you are with the arithmetic at this stage. All right, let's see, what else can I do here? 22 is a good one. Let's do 22. I'm trying to hit all the possible questions I could get for this. 22 is 3 over the square root of t. 3 over the square root of t dt. All right, now again, just like at the beginning of derivatives, the only rule that I have to work with is the power rule, which means I need this to be written as a power function. All right, so this is going to be 3. This is t to the 1/2 in the denominator, so when I bring it up, it is t to the negative 1/2 dt. All right, so I have to rewrite it that way first. All right, now again, some of you pick up on the arithmetic a lot more quickly than others. So if you're one of those people who's good with the arithmetic, if you don't want to write this step down where you pull this out and you just want to jump right to like this step, that's fine. For right now, I'm going to cater to those who are not so good with the arithmetic. Okay. All right, now I apply the power rule here. So I've got 3 times. I add 1 to 1/2. I'm sorry, I add 1 to negative 1/2. And when I add 1 to negative 1/2, I get positive 1/2. So this is t to the 1/2 divided by 1/2 plus c. All right, so this is going to be 3 times. I invert this one and bring it up, so that's 2 over 1 t to the 1/2 plus c. All right, and then I can multiply this. So this is 6 t to the 1/2 plus c. Now here's the nice thing about every single one of these. All right, I can check them because I know how to take derivatives. All right, so I would check this by taking the derivative of this, right? You bring the 6 down, and I have 6 over 3, x to the 6 minus 1, 5. 6 over 3 is 2, so that's 2x to the 5th. All right, over here, I would bring the negative 6 down. That would become negative 7, and negative 6 over negative 6 over negative 2, or negative becomes a positive 6 over 2 is 3, so I get 3t to the negative 7th, all right? You can check these, all of these, every single one of them. No reason to get anything wrong, okay? All right, so let's run through and let's do a couple where I have addition and subtraction. All right. Let's start with a simple one. I'm going to do number 24. All right, and number 24 is 1 plus u squared du. Okay. All right, so my sub-rule for the power rule is that if I have addition or subtraction, I can distribute my antiderivative. All right, so what I really have is the antiderivative of 1 du plus the antiderivative of u du plus the antiderivative of u squared du. All right, so now I just do each one of these individually using the power rule or the rule for constants, right? So the rule for constants is I get the variable back times the constant. All right, so the antiderivative of 1 du is going to be u. The antiderivative of u, well, this has an exponent of 1, so I add 1 to the exponent and divide. So that is going to be u squared over 2. All right, the antiderivative of u squared, all right, power rule. I add 1 to the exponent and I divide. So that becomes u to the 3 over 3 plus c. All right, and yes, doing antiderivatives is almost always going to lead you to fractions. You're going to have to deal with that. All right, how about... All right, I'm going to jump to 32, then I'm going to backtrack a little bit. All right, so let's jump to 32 here. And we're going to do the antiderivative of 6x to the 3rd plus 3 over x squared minus x dx. All right, so again, I'll step through this. right? The first thing that I need to do is make sure that I have the sum or difference of power functions, which right now I don't because of this term right here. All right, so the first thing I want to do is to rewrite this. So that's going to be 3x to the negative 2 minus x. So really that's x to the first dx. All right, now, rather than writing all these individual steps here, I'm going to go through this as if we know what we're doing, okay? All right, so the first thing I need to take the antiderivative of is 6x to the third. So that means I'm going to get 6 times the antiderivative of x to the third, which I add 1 and divide. So that becomes x to the fourth over 4 plus the derivative of 3x to the negative 2. So I'm going to get 3 times the derivative of x to the negative 2, which is going to be x. I add 1 to negative 2 and get negative 1, and I divide. All right, minus the antiderivative of x to the 1. All right, so I get x, I add 1 to the exponent and get 2, and I divide, plus c. All right, I don't have room to continue that way, so I'll just go down here. All right, so now I need to basically clean this up. I'm done with the calculus. Let's just clean up the what amounts to the arithmetic here, okay? So I can reduce 6 and 4, right, by 2. So that's 2, that's 3. So I get 3. Now I can either write 3x to the fourth over 2, or I can write 3 halves x to the fourth. All right, plus, actually minus, let's see if my eraser is going to work. Yes, okay. Weird. I have 3 over negative 1. So that's going to be minus 3 x to the negative 1 minus, and now I can leave this as x squared over 2, or I can write 1/2 x squared plus c. I would be happy with that. If you go to check your answer in the book, they're probably not going to leave a negative exponent. All right, so they are probably going to rewrite this way, 3 over x. Either one of these is fine. Okay, so, all right. So there's one more function that we can look at here, and that is the exponential function. All right, so do I want to go back up here where I have the formulas? Yeah, what the heck. All right, let's go back up here where I have the formulas, and let's throw in number 4. And this is, again, the easy one, because what is the derivative of e to the x, right? The derivative of e to the x is e to the x, which means the antiderivative of e to the x is e to the x. I did tell you when we did that that would be the easiest formula you ever had to deal with, and I believe that is still true. Okay, so if I want to do, let's do one more problem here. And I had at least one of these that involved an e to the x. Yeah, okay, let's do 30. 30 is a good one. All right, so we'll go back to number 30. 30 is 2 plus x plus 2x squared plus e to the x. All right, so if we go at this one term by term, the antiderivative of 2, right? The antiderivative of a constant is the constant times the variable. All right, so this becomes 2 times x plus x is x to the first. All right, so I have to use the power rule on that. So I add 1 to the exponent and divide. 2x squared. So that's going to be 2 times the antiderivative of x squared. Right? So I add 1 to the exponent and I divide. So that becomes x to the third over 3 plus e to the x. The antiderivative of e to the x is just e to the x plus c. All right, so I can clean this up a little bit. There's not a whole lot I can do, but I can at least write the fractions down. So 2x plus 1/2 x squared plus 2/3 x to the third plus e to the x plus c. All right, and that would be that. Now, what if you don't have power functions? All right, so there's a couple of different ways you could not have power functions. Let me get to a new page here. All right, one of those is if you have notation like a square root or cube root or something like that. All right, we've already seen what to do with that. If you have a product or a quotient, you have to be able to reduce your product or a quotient to the sum or difference of power functions, just like when we first started derivatives. All right, we do not have a product and quotient rule for antiderivatives. We're going to learn a small piece of how to deal with more complicated functions, but most of that is going to go on for you guys in Calc 2. All right, so let's take a look at... All right, both of these give you hints. All right, do I have one that doesn't give you a hint? All right, I'll just do one that gives you a hint. Okay, let's take a look at number 38. I'm still in the same section. All right, number 38 is the antiderivative of x to the fourth minus 1 over x squared. All right, now, I don't have an antiderivative rule that will let me do anything with something that looks like that. I only have a power rule, all right, which means I need to do some algebra to this before I can take the antiderivative. All right, so I need to use the distributive law. Like that. All right, distribute that x squared in the denominator, and then reduce the fractions where I can. All right, so this is going to be x to the fourth over x squared is x squared. 1 over x squared becomes x to the minus 2 dx. All right, so now I have it as, in this case, the difference of power functions. So I can use the power rule on this part, right? I add 1 to the exponent and I divide. So that becomes x to the third over 3 minus, here again, I add 1 to the exponent and I divide. So I add 1 to negative 2 and I get negative 1 over negative 1 plus c. All right, then I just kind of want to clean it up a little bit. So 1/3 x to the third. Minus and minus is going to become a plus. And x to the negative 1 becomes 1 over x plus c. All right, so I can deal with a quotient as long as I can reduce that quotient into the sum or difference of power functions. Okay, so for right now, you can only have a monomial, a single term in the denominator. All right, as long as you have that, then you can work the problem. What else could we do here? If I have a product... All right, here, let's do this one. I think number 40 is going to be my last one. I think that'll give you enough to work with. So let's do number 40. Is the antiderivative of u to the negative 2 times 1 minus u squared plus u to the fourth du. All right, so again, I don't have a rule that allows me to take the antiderivative of the product of two functions. All right, so I have to multiply that out. All right, which means in this case I need to distribute this. Whoop, that should go over there. I need to distribute it that way. All right, so okay, so let's go back here. U to the negative 2 times 1 is u to the negative 2. U to the negative 2 times u to the 2. Well, what happens? I add the exponents and I get 0. So u to the 0 is 1. Plus u to the negative 2 times u to the 4th. Again, I add the exponents and I get 2. U squared. All right, so there I have the sum or difference of power functions, and now I can work the problem. All right, so I take the antiderivative of u to the negative 2. All right, so I add 1 to the exponent, and I get negative 1, and I divide. The antiderivative of 1 is 1 times u, so that's u. The antiderivative of u squared, I get u. I add 1 to the exponent, and I divide. Okay. All right, so the only thing I have to do really is just clean this up a little bit, and there's not much to do. This is going to become negative, and that's going to become 1 over u. So negative 1 over u minus u plus 1/3 u to the 3rd plus c. All right, I'm going to stop here because I think you have enough to look at in order to do the homework that I'm going to post. So I will post the homework, and I will post the video, and I will post the PowerPoint slides, and when you're done with the test, you can start working on this.